All right, so you know how much we all use Google Maps,
Right.
right? Like, it's pretty amazing how it can get you anywhere you need to go.
Yeah, absolutely. It's become such an essential tool for so many people.
But have you ever, like, zoomed in and out on Google Maps and wondered, how does it even work? I mean, how does it navigate that crazy web of streets and traffic and everything?
It's honestly a pretty mind-blowing feat of engineering and math.
Well, that's what we're diving into today. We're taking a deep dive into the mathematical genius behind Google Maps. You send over that essay, Google Maps is a graph, and I have to say, I'm ready to have my mind blown.
Well, hopefully we can shed some light on how it all works, because at its core, Google Maps is based on this concept called graph theory. It's basically this idea of representing information as a network of points connected by lines.
Okay, so is it really that simple? Like just dots and lines?
Yeah. Well, it is in a way, but the scale and execution are what make it so incredible. Think of it this way. Cities, intersections, landmarks, those become our nodes on the graph. And the roads connecting them, those are the edges. So it's like this massive interconnected web spanning the entire globe.
Okay, I'm starting to see the bigger picture here. So it's kind of like when you map out a social network, right? Each person is a node, and their friendships are the connections or edges.
Exactly. That's a great analogy.
But how does Google Maps actually know where to put those nodes on an actual map?
That's where vectors come in. You know, latitude and longitude, those coordinates we use to locate places. Well, those act as vectors, giving each location a specific point in space with direction and magnitude.
So it's not just showing points on a map, it's actually using math to understand their relationships to each other.
Precisely. And those relationships are key to how Google Maps figures out the best routes.
Because I'm guessing not all connections are created equal.
You got it. Think about it. A highway lets you travel much faster than a congested city street.
Yeah, of course. But how does Google Maps actually factor that into its calculations?
Through something called weighted edges. Each edge or road is assigned a weight representing the cost of travel.
So like time, distance, traffic, all that.
Exactly. And this is where it gets really interesting. This weighting system is how Google Maps figures out the fastest route, not just the shortest distance.
So a highway might have a lower weight because you can zoom along while a traffic jam side street gets a higher weight.
Exactly. It's considering all those real-world factors to make sure you get where you need to go as quickly as possible.
Wow. I never realized how much thought goes into something I use almost every day. But how does it actually crunch all those numbers and find the best path through that massive graph?
Well, that's where the real magic happens.
It's algorithms.
Specifically algorithms like Dijkstra's and they're the brains behind the operation, constantly working to find the most efficient path.
Okay, I always hear that word, algorithms, but honestly, they always seem kind of mysterious to me.
They sound complicated, but really they're just step-by-step instructions for solving a problem. And in this case, the problem is finding the best route through that massive graph of nodes and edges we've been talking about.
So how do these algorithms actually work?
Well, let's start with Dijkstra's algorithm. It's kind of the classic, the original path-finding algorithm. What it does is systematically explore the graph, calculating the shortest path from your starting point to every other node.
So it's checking every possible route. Wouldn't that take forever with a graph as huge as Google Maps?
It can be a bit computationally intensive, but Dijkstra's is actually very clever about it. It keeps track of the shortest distances it finds along the way and uses that information to avoid unnecessary calculations.
So it's not as brute force as it sounds.
Right, but even with its efficiency running Dijkstra's on a graph, the size of Google Maps could still take quite a bit of computing power.
So that's where A comes in.
Exactly. May is like Dijkstra's smarter, younger sibling. It uses something called a heuristic, which is basically an educated guess based on available information to estimate the distance to the destination.
So instead of checking every single path, it focuses on the ones that seem most promising.
It's like if you're driving to a new city and you see a highway sign pointing towards your destination, you're more likely to take the highway than some random side street, right?
Yeah, that makes sense.
ME uses that same logic to speed up the search process.
So how does it know which paths are more promising?
It combines the actual distance traveled so far with that estimated remaining distance to the destination. It's constantly balancing those two factors to make the smartest decision at each step.
So it's like it's learning and adapting as it goes.
Exactly. And remember those weighted edges we talked about. MF factors those in as well. Traffic, road closures, all those real-time conditions are taken into account to get the most accurate travel time.
It's kind of freaky how good it is at finding the best route, even with all those variables.
Well, it's not magic, it's math. But it is a testament to the ingenuity of the people who developed these algorithms. They took this incredibly complex problem, broke it down into steps, and created a system that can navigate a world of constantly changing information.
It's mind-blowing to think that all this is happening behind the scenes every time I open Google Maps.
Yeah.
And we rely on it for so much these days, driving, ordering food, even just exploring a new city.
And we've only just scratched the surface. As technology continues to evolve, these algorithms will only get more sophisticated, more efficient, and even more seamlessly integrated into our lives.
Makes you wonder what the future holds for navigation and the power of graph theory to connect us to the world around us.
It's a fascinating time to be alive, that's for sure.
It really is. But we still need to talk more about those algorithms in detail. They seem to be the real heroes of this story.
They are indeed. And we'll get into the nitty-gritty of how Dijkstra's and A work their magic right after this.
All right, so we've got this massive graph representing the entire world with nodes and edges and algorithms working behind the scenes. But how does it actually help us find things in the real world? Like, how does it know where all the restaurants and gas stations and museums are?
Well, that's where those points of interest come in. Remember, everything in Google Maps is a node on that giant graph. Restaurants, gas stations, museums, you name it, they're all nodes connected to the larger network.
So when I search for, like, pizza, Google Maps is basically searching that graph for pizza-related nodes near my location, which is also a node on the graph, right?
Exactly. And it uses those weighted edges we talked about, the distances and travel times, to rank those pizza places based on how easy they are to reach.
So it's not just finding the pizza place that's geographically closest to me, it's finding the one that's easiest to get to considering traffic and everything.
That's right. It's all about finding the most accessible option.
That's pretty smart.
And it goes beyond just searching for a specific place. Imagine you're on a road trip and need to find a gas station along the way. Google Maps can analyze your path through the graph, identify gas station nodes along the way, and even suggest the most convenient ones based on your estimated arrival time.
Hold on. You can predict when I'll need gas and suggest the best stops along the way. That's like some next-level stuff.
It is pretty impressive, right?
So we've talked about personal navigation, but I'm curious about how this graph is used in other ways.
Well, think about delivery services like Amazon or FedEx. They rely heavily on Google Maps and its graph data to optimize delivery routes, making sure packages arrive on time and efficiently.
Yeah, that makes sense. With all those packages zipping around cities, they need a way to navigate that complex web of streets.
Exactly. It's like a giant real-world connect-the-dots game with real-world consequences.
But it's not just about efficiency, right?
No, it's not. This technology is also being used in urban planning. By analyzing traffic patterns and identifying bottlenecks in the graph, city planners can make informed decisions about road improvements, public transportation routes, even the placement of new businesses.
Wait, so Google Maps can help plan cities?
In a way, yes. They have access to so much data about how people move around a city. By analyzing that data, they can see where traffic gets congested, where people are traveling to and from, and even predict how changes to the road network might impact traffic flow.
That's incredible. I had no idea. A simple concept like a graph could have such far-reaching applications.
Yeah.
We talked about personal navigation, delivery services, urban planning. Is there anything this technology can't do?
Well, it's important to remember it's just a tool. It's up to us as users and as a society to think critically about how this technology is being used and to be mindful of its potential impact.
That's a really good point. It's easy to get caught up in the wow factor and forget about the bigger picture.
Exactly. And that's why deep dives like this are so important. The more we understand about how these technologies work, the better equipped we are to use them responsibly and to shape their development in a way that benefits everyone.
So the next time I use Google Maps, I'll be sure to take a moment to appreciate all the complexity happening behind the scenes, the nodes, the edges, the algorithms, the sheer brilliance of the people who made it all possible.
And perhaps you'll even start to think about the broader implications of this technology and its impact on our world.
Absolutely. It's not just about getting from point A to point B anymore. It's about understanding the interconnectedness of our world and the power of math to help us navigate it. But we still need to talk about those algorithms in more detail. They seem to be the real heroes of the story.
They are indeed. And we'll get into the nitty-gritty of how Dijkstra's and A work their magic right after this.
Okay, so let's talk about those algorithms. We keep mentioning them, but I think it's time to really break them down. Dijkstra's and A, what are they all about?
Well, like we said earlier, algorithms are basically just sets of instructions for solving problems. And in the case of Google Maps, the problem is finding the best route through that giant graph of nodes and edges.
Right, so how do they actually work?
Well, Dijkstra's algorithm is like the classic, the tried and true method. It systematically explores the graph, calculating the shortest path from your starting point to every other node.
So it's checking every single route possible. Wouldn't that take forever on a graph as huge as Google Maps?
It would if it did it blindly, but Dijkstra's is smarter than that. It keeps track of the shortest distances it finds along the way and uses that information to avoid unnecessary calculations.
So it's like it's learning as it goes,
Yeah,
becoming more efficient.
exactly. And that's what makes it such a powerful algorithm.
But you mentioned that even Dijkstra's can be a bit slow on a graph the size of Google Maps. Is that where A comes in?
You got it. A is like Dijkstra's, but with an extra layer of intelligence. It uses something called a heuristic, which is basically an educated guess based on available information to estimate the distance to the destination.
So instead of blindly checking every path, it focuses on the ones that seem most promising.
Exactly. It's like if you're driving to a new city and you see a sign pointing towards your destination, you're more likely to follow that sign than just wander around aimlessly, right?
Yeah, of course.
A-La-Man uses that same logic to speed up the search process.
So how does it know which paths are more promising?
Well, it combines the actual distance traveled so far with that estimated remaining distance to the destination. It's constantly balancing those two factors to make the smartest decision at each step.
So it's kind of like it has a sixth sense, always looking ahead and anticipating the best route.
It's not magic, it's math. But it's definitely impressive how well it works.
It is. And to think it's all happening behind the scenes every time we use Google Maps.
That's the beauty of it. It just works seamlessly in the background.
It's amazing how much we rely on these algorithms these days, not just for navigation, but for so many other things.
Yeah, it's pretty incredible when you think about it.
Well, this has been an incredible deep dive into the hidden world of Google Maps. I had no idea it was so complex and fascinating.
It's one of those things we take for granted, but there's so much going on beneath the surface.
Thanks for taking the time to explain it all to us.
My pleasure. I'm always happy to talk about the power of math and algorithms.
And to our listeners out there, next time you fire up Google Maps to find your way around, take a moment to appreciate the incredible technology that's making it all happen. It's a testament to human ingenuity and the power of mathematics to solve real-world problems. Until next time, happy navigating on.
For more short-form podcasts like these, please like and subscribe. The top comment on this video will be the topic of our next podcast. Goodbye.